Again, I'm making the same mistake. No screen. Wait, please. Okay, done. All right. So for nuclear physics, we are. It's a very basically a very nice chapter, very soothing. So I think you guys will like it too. So the first thing we should always remember is the law of conservation of mass and energy. So we have basically read about law of conservation of energy a couple of times, but actually mass is conserved while mass and energy are very closely related, which means that this law is truly defined as the energy can neither be created nor destroyed, but it changes to one form to another. That's how it does, right? When we talk about one form to another, basically what we mean is that not only the energy form, but mass can change into energy, or energy can also change to mass. Okay? So, there are few things that you guys need to remember, that the mass of proton has a very specific value, which is 1.00. It's even more like more decimal places precise than this, but we will take like 4, 5, 6 decimal places. Mass of neutron is about 8665 U, and mass of electron is 0.00055 U. Now you might be wondering what this is, right? U is the unified atomic mass unit, as you know, and these are basically called the rest masses, which means when they do not have any kinetic energy. So now, unified atomic mass. So we already know the definition, but I'm going to write it. I wrote it in ideal gases, if I'm not wrong. Basically, it is the standard mass of the atomic particle. In fact, atomic particles, and is equal to 1/12 of mass of carbon 12 atom, which is basically equivalent to 1.66 times 10 raised to power minus 27 kgs. You already know this. Then we should know about the relative atomic mass, and the relative atomic mass is basically defined as mass of an atom that is the ratio of the rest mass of the atom to the unified atomic mass. All right. So it's just that when you write something like, carbon 14 6, so this 14 basically means 14U, which is the relative atomic mass, right? Like that. Is there any questions? Please let me know that I can help with. All right. You can write it down, please. Okay. The next thing we're going to do is basically the nuclear binding energy. So, nuclear binding energy has two definitions. Now, you can follow any definition you like, but it's up to you. Both are correct. Nuclear binding energy of a nucleus defined as, I had to write is, defined as the amount of energy released when an atom is formed from its constituents, like that. Okay, so uh, well, in fact, you can write constituent particles. That would be even better. All right, so this is one of the definitions, or you can write it is the amount of energy required to break up a nucleus into its constituent particles. So basically, both mean the same thing. Like when the formation is happening, uh, basically energy is released, and to break up a nucleus, you need to give energy. This amount is the same, and it is nuclear binding energy. Remember that this is a scalar quantity, and the symbol we use for this is delta E. Okay. All right. Hello Hassan Atik. Hello Raman. Okay, now everyone, if you have any questions, let me know here. I think these days your school is too hard on you. That's why you guys are so tired and not talkative at all. Am I right? Aman, are you tired today?
Yeah, sir, kind of preparing for an exam.
When? What exam? Tomorrow?
Yeah, I'm giving October, November for Chem, so it's next week.
Oh, oh, all right. Now, it's all right. Good luck with that. So often it is measured in mega electron volts rather than in joules. So you will find all of them, like all the time, mega electron volts. Now, what exactly is this MeV? In AS, we learned that 1 electron volt is equal to 1.6 times 10 raised to minus 19 joules. You need to remember that. So 1 mega electron volts is basically 1.6 times 10 raised to minus 13 joules. So mega means 10 raised to power 6, right? So that's fine. Now you got to remember that. Right. Now, then there is something called the mass deficit or defect. So basically, these are two words you're going to use all the time. They mean the same thing, really. And mass deficit or defect means that it is defined as the difference of mass of a bound atom and the total mass of the constituents that make up that atom. It is a scalar quantity. And then the symbol is delta M. Alright. How many of you understood this? Please let me know. Okay. Now, so basically, I'll ask it from Suman. Suman, have you ever wondered that if protons hate each other so much, how can they live together in a tiny nucleus?
Sorry, sir, could you repeat?
If protons hate each other so much, how can they live together in a tiny nucleus? That's my question.
I don't know, sir.
Okay. Gatika, what do you say? How can they live together then?
Sir, I have no idea.
You've never thought about it. Why have you guys not thought about it? Why haven't you asked this from your chemistry teacher? Why? All your life you've been told that proton is a positive particle and it repels positive. How is it possible that in a nucleus all of them are positive except for the neutrons which are neutral? Doesn't really matter. Okay. Rafe, what do you say? All right. So it happens because I'm going to tell you something very, very important. So, once upon a time, there lived two rich people in their separate houses. Okay. And those two people hated each other. So, both of them had the same type of house, the same type of car, everything was the same. But they lived separately because they had a lot of money, which makes them rich, right? So then the crisis hit, and when the crisis hit, all of them, or everybody got really poor. And now, when they got really poor, so that poverty made them stay at one place to share the expenses, right? because now it's important to eat before fighting. So, what we do is we take that certain chunk of mass away from them and then convert that into energy. Energy is released, and because now they don't have any money, they have to live together. Do you guys understand what I'm saying? So now let's look at the example from this, that how we have made protons compromise with each other. So, example. So first of all, it says find the mass defect in helium 4 2. So this is the helium mass number and proton number. Now, helium has 2 protons and 2 neutrons. According to the rest masses that we've seen above, we can find the 2 proton mass would be 2 times 1.00767 U, and for neutron it will be 2 times 1.008665 U, just like that. Now, the thing is that the total mass, if we combine these to form a new helium, so total mass of constituents, which is also known as the expected mass, because this is the real mass that they have and we want to, we are combining them. So the expected mass would be, if you multiply and add them together, it's going to be 4.031882 U. So even in the exam you have to write many decimal places to be precise, okay? However, the actual mass of helium nucleus is basically equal to 4.001508 U. You can Google it as well. So after formation, the helium has less mass than what we expected it to have. Okay. Now this shows that when it was formed, there was some kind of mass defect that happened. Mass was gone. So we're going to find that. And then it became 0.03037 U. Okay. Now, so basically, what has happened to this mass is that according to Einstein, equation, delta E is basically the mass, energy. The mass has changed into energy. So this is basically the nuclear binding energy. So this is the energy that was converted from mass, and now it is released, so it has basically bound the nucleus together, so made it poor. Is it clear, everyone? Any questions? Please let me know. Now notice that when we're looking at the helium nucleus, we're not including electrons in this. But suppose that in a question he says that determine the binding energy of a carbon 12 atom. Now, if it's written atom, so we already know that the mass of an atom of carbon 12 is equal to 12.0000000 U. Right? Now, so we want to find the binding energy. So first of all, what we're going to do is we're going to find the mass of carbon nucleus, because the nucleus forms and then the electrons basically start revolving, right? Like that. So actual mass, what you're going to do is you're going to do 12.0000000, and then you're going to subtract the 6 electrons it has. Electrons have a rest mass of 54858. All right, like that. So actually the carbon has about 11.996709 U. That is the actual mass of an carbon nucleus. All right, carbon 12 nucleus. But now, to find the binding energy, we must also find the expected mass of carbon 12. So the expected mass is like it has 6 protons. So 6 protons are like that, which is 6.043656U, and it has 6 neutrons, which is 6 into 1.008665U. So that's 6.05199U. And then the expected mass should be like, if you add them together, it should be about 12.095646U. So actually we are like short of some mass, as you can see from our expectations. So the mass deficit would be 12.095646U minus 11996709. Because the mass deficit is so small, we have to take so many, you have to be very precise with the values. So this will be 0.098937U, like that. Now from this point onwards, you have 2 paths to go to find the nuclear binding energy. So let's find that. First, we are going to look at method 1. And you can attempt that, okay? So method 1 is the change in mass in kg. We could convert that. Whereas in U, we can do 0.098937 times 1.66 times 10 raised to minus 27 kilograms. So we've changed U into kg, and we get 1.642354 times 10 raised to a minus 28 kg. So this is the change in mass, okay? And then we can simply use delta E equals to mc square, where we have found it. To use this equation, you must convert the mass into SI units. There is no other way. So speed of light is this. So we're going to end up with 1.478 times 10 raised to minus 11 joules, like that. The method 2 is a bit different. I'm going to use a different color. So sometimes in the exam, he's going to give you a value of 1U. So the standard value is this, but it could be a little different if he gives you some value, but it will be 930, maybe 932, something like that. So this is a standard value. So what you're going to do is that if 1U is 931.5 MeV, so we can say that the change in energy will be equal to 931.5 MeV multiplied by delta M. So from this formula you can find this value. That's very simple. You just multiply 935, and instead of changing into kg, you just need to multiply the value in U. That's the good part of this, that you don't have to do the step where you have to convert it to kg. And this is going to give you 92.3 MeV. In this method too, do not use E equals to mc square. That would be wrong. Is it clear? Even if you want to convert like this value to suppose MeV, so converting joules to MeV, how do we do that? Pretty simple actually. So you say that whatever it is in joules, you just divide it by the value of EV, and this will give you 9.226 something like that into 10 raised to 7 EV, and then you can convert to mega, so then it will be exactly the same, because 92.3 10 raised to power 6 EV, and then you can just replace 10 raised to power 6 to mega. That's how we can do it. So basically both of them give you the same answer, but at the end method one is a bit longer, but it depends what kind of values they have given to you, so you have to follow and learn both of them. All right, you guys have any questions, please let me know.
And the final answer should be in terms of MeV.
Like 99.9% of time he's going to ask you in MeV.
And the mass deficit, it will be in terms of U, right?
99.9% of time, that's correct.
Okay.
So for method 2, there is no possible way of further converting it into joules?
There is, why not? If he says you want to convert it into joules, all you got to do is like I'm going to write it here. You can do 92.3 times 10 raised to 6 EV. Now you can replace EV with joules by just multiplying it with 1.6 times 10 raised to minus 19 joules. It will give you the same answer then. Do you understand that?
Yes, sir, thank you.
So the thing is that our goal of this chapter is like it will be very rare that you're going to convert EV into joules, but it will be often that you will be converting joules to mega electron volts. So that's how you should, work it. Okay. Okay. Now, I just want you people to do something. Okay, so I want to give you a question. You can try it out, and then from there, we're gonna do an example, and then from the past paper, so you see how the questions are, and then we'll move forward tomorrow. Because for tomorrow's work, we need more time. So binding energy of helium for atom in mega electron volts, that's what we need. So what they've given is they have given you the actual mass of helium, which is 4.00. Helium nucleus हम लिख लेते हैं. This is nucleus by the way. 1508U, and the expected mass. So basically, I don't want you to solve the other things. Expected mass of helium nucleus is 4.031882 U. So I just want you to find, this is for nucleus, okay? Do not confuse it with mass. Alright, so I just want you guys to find the binding energy of this quickly, please. I just want to remind you that you do not have the 931.5 given to you, so you have to follow method 1 in any case. I'll show the method 1 as well so you can compare when you're doing it, please. Hurry up, it should take you like 2-3 minutes.
So here is the answer 2.7 times 10 power 15.
2.7 times 10 power 15. You're telling me in what? Joules?
Joules, yes.
No, I want in MeV. I written it. Find it.
Okay, sir.
So is it 2.84 into 10 raised to minus 25?
In MeV? No,
Yeah.
no, no. That's wrong. That is absolutely wrong. So, can you confirm what was the change in mass you're getting? The mass deficit?
So 0.030374.
Yeah, that's correct. So this is like 882 U minus 4.001508 U, and then you should be getting like 30374 U. And then when you find delta E, which is equal to m delta m times c square, so this should be converted, so I'm going to do it directly, into kg first. So this is the delta m, right? Multiplied by 3.0 times 10 raised to 8 whole square. And then divided by, because this will give everything in joules. So if you want to convert it into mega electron volts, you must divide it by 1.6 times 10 raised to minus 30, because that's 1 MeV, right? So when you do that, your answer should come out as 28.36 MeV. Check with the calculator as well. Okay.
So could you explain that again, please? Sir, after the change in mass or the mass deficit.
Okay. So this is basically this section that you see here. Like, let me highlight this. This section. This is change in mass. Do you understand? Because
Yes, sir.
when you convert U into joules, you got to multiply 1.6 times 10 raised to minus 27, right? 1.66 actually. Let me write it in nicer way. 1.66, right? Is it clear? Then C square,
Yes.
you know it's this. Now, this whole section that you see, this whole, oh, why isn't it writing? Okay, is in joules, right? Now, to convert joules, you got to multiply into EV, you got to divide it by 1.6 times 10 raised to minus 19. Instead of doing that, what I did was I divided by 1.6 times 10 raised to minus 13 to get me the direct answer in mega electron volt.
Okay, sir. All right. Thank you.
Do you get my point now?
Yes,
Okay.
sir. Yes.
That's how I got this answer. Probably you guys had. Let's try. All right. Okay. Done. All right. So I guess this would be it from my side today. All right. I just want you guys to do these questions again when you're like doing it, okay?